Welcome back to the lecture series of number system and codes. In today's class, we will learn how to represent a signed binary number. There are three methods that we will learn in today's class with examples. We are already familiar with decimal number system. In our school, we have solved many mathematical problems with decimal numbers, and we also dealt with natural numbers. But there we have seen that all the numbers were positive numbers. But there are scenarios where we may need to deal with negative numbers as well. In the number system, we have the provision that we can mention the sign of that number. So if the number does not have any sign, be it positive or negative, then that number is called unsigned number. And the unsigned numbers are always considered as positive number. Suppose if I say 30, we know this is a decimal number and this is a positive number. Why it is positive? Because we have not though we have not mentioned any sign, because if no sign is mentioned before that value, that magnitude, then by default it is taken as positive number. But if we are dealing with signed number, be it positive or negative, then we have to mention the sign of that number before the magnitude, before the value accordingly. Suppose if we are dealing with, or if the number is a positive number, suppose if it is, the value is 30, and if we want this to be a positive number, then we have to mention plus sign before that number, and that's how we do in case of decimal number system. Now suppose if it is a negative number in case of decimal number system, and again if the value is 30 but it is this time a negative number, then we have to mention the negative sign before that value or magnitude. But that's what happens in case of decimal number system. But in today's class we will be learning how to represent a signed binary number. In case of binary number system, there is no concept of mentioning plus or minus sign before the magnitude of that number. There the representation or the technique is different, and that we will be learning today. If it is suppose signed binary number, again in binary number system also there are two types of numbers: signed number or signed binary number and unsigned binary number. Suppose if we are working with, you are dealing with signed binary number, then in that case the MSB, most significant bit, is used to represent the sign of that number. Suppose we have a 4-digit number like this, 1011. So this is a 4-bit binary number. In that case, if it is a signed binary number, we will be using this MSB to store the sign or to represent the sign of that number, and rest of the bits will be used to represent the value or magnitude of that number. Now the question comes, then what should be the value if the number is positive or negative? The rule is, if the MSB is 0, then the number is positive, and if the MSB is 1, then the number is negative. That means the example that I have taken here, as I said, this MSB represents the sign. So here, since this MSB is 1, so our number will be negative, and 0, 1, 1 is our magnitude. So if we go by this convention, then 0, 1, 1 we know that is equivalent to 3 in decimal number system, so it will be -3, and that we will be learning next, the three methods of representations. So in case of binary number system, there are three methods or three techniques to represent a signed binary number. The first technique or first method is sign magnitude representation. We will see next that how we can represent a signed binary number by using this technique. This method is easy, that I have just talked about. Here again, MSB represents sign and the remaining bits represent the magnitude of that binary number. Now as we can see here in this format, here we have 8 bits from B0 to B7. So this is a 8-bit binary number. So if it is a 8-bit binary number, then B7 is the MSB and that will tell us that what is the sign of that binary number, and the remaining bits means from B0 to B6 that will be used to represent the magnitude of that number. Now here again the rule we know that if the MSB is 1, then the number is negative, and if the MSB is 0, then the number is positive. So suppose if we take this as example, so here as we can see this is a 6-bit binary number. So if we are using this method, sign magnitude representation, then this MSB will be used to represent the sign, and the remaining bits from 0 to 5th bit that will be used to represent the magnitude. So as per this representation, since the MSB is 0, so this number will be a positive number, and then we have to see what is the decimal equivalent of the other part of that number, and accordingly we will be able to answer. Next, if we take this example, suppose, so here as we can see again we have taken 6-bit binary number, so this will be used as sign. So here 1, so 1 means MSB is 1 means the number is negative, so this number will be negative. This, the previous example, the number was positive, and the rest 5 bits will be used to represent the value or magnitude of that number. And now if we want to know what is the decimal equivalent of this number, then easily we can map with the decimal number system and we can answer. Now suppose if the binary number is not a signed binary number, if it is an unsigned binary number, and if the number still has 8 bits, then what will be the equivalent decimal number, the maximum value in the decimal number system that it can represent? We know the rule, that is the radix in binary number system or base value is 2, and if that number has 8 bits, so 2 raised to the power 8 means 256, and 256, so it will start from 0 and the maximum value will be 255. So if it is an unsigned binary number, then in decimal number system it can represent from 0 to 255, but if it is a signed binary number, then that value will be divided into 2 parts, because we will be representing positive as well as negative numbers, and at the same time the last digit, the MSB, will be used or will be reserved to represent the sign. So suppose if again we are using 8-bit binary number, but in that case since MSB will be reserved to represent the sign, so maximum number of bits that we will be using or will be able to use, that is 7. So maximum decimal value that we can represent by using those 7 bits is 128, right? So here as we can see this is a 8-bit number where the MSB is 0, so that represents this is a positive number, so this represents positive sign. And now if we consider the remaining 7 bits from 0 to 7, then all the values are 1, and we know in the decimal number system that represents 127. So using 8-bit binary number, signed binary number, we can max represent plus 127 in the decimal number system. Now suppose if we take this example, then here also we can see we have 8 bits. This is a 8-bit binary number, so MSB will be reserved for sign, and since this is 1, so this will represent that this binary number or signed binary number is a negative number, and the remaining bits from 0 to 7 that will be again used to represent the magnitude. Again we have all ones in all the 7 positions, so this represents 127. So basically this is the equivalent of minus 127 in the decimal number system. So if the signed binary number has 8 bits, all the 8 bits we cannot use to represent magnitude. MSB will be used to represent sign, and the rest 7 bits will be used to represent magnitude, and that's why this time it is half. It is 256 divided by 2, it's 128, and since we will be starting from 0, that's why 0 to 127. And on the negative half, again if it is 8-bit binary number, then the MSB will be used to represent the negative sign, and the rest 7 bits we will be using to represent the magnitude, and this time it will be minus 127. Again 128 So from 0 to 127. And in case of sign magnitude representation, we have the concept of positive 0 and negative 0. That's why in the positive half it is 127, and also in the negative half it is minus 127. Now suppose if we generalize, if suppose it is an unsigned binary number and if we have n bits, so in case of 8 bits, what we have seen, 2 to the power 8, and that is 256. So 0 to 255, that means maximum number is 255 is what, 2 raised to the power 8 minus 1. So if we generalize, then it will be 2 raised to the power n minus 1. Now if it is a signed binary number, then what we have seen, that it will be, instead of 256, the maximum count will be 128, and since it will start from 0, so it will go till 127. So in place of power, if we take 1 less, so initially it was 8, now if we take 1 less, so if it is 7, then the count becomes half, from 256 to 128. And then since it is going from 0 to 127, again the maximum count minus 1, and that's why it is, again we are subtracting 1 from here. So that is on the positive half. And since on the negative half also, for negative numbers also we are using the same concept, so here again we will be using the same formula. Since 1 bit is reserved for sign, that's why it will be 2 raised to the power n minus 1 and then minus 1 again. This method will be more clear when we will be using a few more examples. Now the next method is about 1's complement representation. I have already taken a separate class to find 1's and 2's complement of a binary numbers, so you can refer that class. This 1 complement representation and next 2's complement representation, they are mainly used to represent a negative binary number. For positive binary number, the 1's and 2's complement of a given number will be same. Only it will differ when the number is negative number. So first we have to know how we can find 1's complement of a given binary number. Suppose we have a number like this, 1011, then how we can find 1's complement of this given number? We know that we have to subtract from a number having same number of bits, and in every position we have value 1, which is the maximum possible value in binary number system. Then from that number we have to subtract the given number. So this way if we subtract, then what we will get, 0 in LSB position, then 0, then 1 here, and here 0. So this is 1's complement of this given number. So one thing what we have noticed here, that 1's complement of 0 is 1 and 1's complement of 1 is 0. So it's very easy to find 1's complement of a given binary number. Simply we have to put 0 in place of 1 and 1 in place of 0. Simple. So here also, if the most significant bit is negative, then that represents that the number is negative number, and if MSB is 0, then that represents that the number is positive number. Now as I said, that if the number itself is a positive number, then we don't have to take any complement for that. Suppose if the number is plus 7, so we know that what is the binary equivalent of plus 7. To represent 7 we need maximum 3 bits, so it will be 1 1 and 1. That is the binary representation of plus 7. And now if we want to represent this plus 7 by using 4 bits, because we need at least 4 bits for sign, we need 1 extra bit. So this number, if we want to represent by 4 bits, then here since this is plus, so we have to take 0 in MSB position. So this will be the representation of plus 7 in 1's complement method. That is easy. But how to represent minus 7? For that, what we do is, first we take plus 7, then we represent that plus 7 in binary number system. So what next we have to do to represent in 1's complement representation? We have to take the 1's complement of this number. So it will be what? So this is the 1's complement representation of minus 7. And here 1 at MSB position, this tells that this is actually a negative number. So to represent a negative binary number, we first took the positive value of that number. So we started from positive number and then we took 1's complement of that positive number. So when we took positive number in MSB position, that digit, the value of that digit was 0. But when we took 1's complement, that value became 1. That means the 1's complement of a positive binary number is negative. Similarly, if the number here in the MSB position, if we have 1, if the number is negative, and if we take 1's complement, then the number, this 1 will become 0 and this negative number now will become positive number. Now we have to see that how many numbers we can accommodate using an n number of bits. So here, as we can see that here we have in total 4 bits, but the last bit was reserved to represent the sign, so only 3 bits were used to represent the magnitude. So again the concept is same as before, the sign magnitude representation. So here if we take suppose 8 bits, then out of 8, 7 bits will be used to represent magnitude, and the last bit, the MSB, will be used to represent sign. It will be from 0 to 127 on the positive side, and it will be 0 from minus 127, or we can say minus 0 from minus 127 on the negative side also. So here in case of 1's complement representation also, we have the concept of positive 0 and negative 0. That means if we generalize the 1's complement representation for n bits binary number, then for positive numbers it will be 2 raised to the power n minus 1 minus 1, and on the negative side also for negative numbers also again it will be 0 to 2 raised to the power n minus 1 minus 1. So on the positive half, if suppose n is 8 bits, then it will be this count, or this formula will give us 127. So from plus 0 to plus 127, and then on the negative side also it will be from minus 0 to minus, and then this count will give us 127. So this is the whole concept of 1's complement representation. Only thing that we have to focus on is how we can represent, or how we can find the 1's complement of a given signed binary number. This is first point. And the second point that we have to keep in our mind is MSB, the last bit, the most significant bit, will be reserved for representing the sign, and the remaining bits we will use to represent the magnitude of the number. And third point is this method is used mainly to represent a negative binary number. So if the binary number is positive, then we don't have to bother. 1's complement representation will be same as the positive number, but if it is a negative number, then we have to take the 1's complement of that positive value. The next representation is 2's complement representation, and that is again used to represent a negative binary number. So what we have to do is first we have to find 1's complement of that binary number, and then we have to find 2's complement. And we know that how to get 2's complement from 1's complement. So if suppose the number is 0101, then first we have to find 1's complement of that number, and that is 1010, and then 2's complement. And for that what we do is we add 1 to that 1's complement, so it will become 1101. So this is the 2's complement value of this given number. And here also MSB is reserved to represent the sign of that number. And here also the concept is same. If MSB is 1, then the sign is negative, and if MSB is 0, then the sign is positive. Now here also again, if the number is suppose a positive binary number, then 2's complement representation of that number will be same as the original number, the binary representation of that original number. Suppose if we have taken 7, so binary equivalent we know again that is 111. So these 3 bits we need to represent the magnitude of that number, and we have to use 1 bit to represent the sign. So here since this is plus, so we will be using 0 here. So this is the binary representation of plus 7, and since this is a positive number, we don't need to find its 1's complement and then 2's complement of that number. 2's complement representation of this positive binary number will be same as 0 1 1. But if suppose if the number is negative, say if the number is -7, then what we have to do? Again we have to start from +7, then we have to take its equivalent binary. So 7 means again 1 1 1. These 3 bits we need to represent magnitude, and for plus it will be 0. So this is for +7. Then from here we have to take 1's complement of that number. So this will become 1 0 0 0. And then from here we have to find the 2's complement. 2's complement means we have to add 1 to that. So it will be 1 0 0 0. This is 1's complement, and then when we will add 1 to that, it will be 1 0 0 and then 1. So this is 1 0 0 1. This is the 2's complement value of this number. So this is 2's complement representation of -7. So don't get confused between these two. This is the original value of +7, the binary equivalent. Then from there we have taken 1's complement, and then from there we have taken 2's complement of this number, and this value 1001 is actually 2's complement representation of -7. So this is one of the ways how we can represent our negative binary number. Now if we focus on this number, the original binary representation, we had 0 in MSB position. Then we took 1's complement, so that became 1, and we took 2's complement, so that is again 1 in MSB position. That means we can say if we take 2's complement, then the MSB value changes, or we get the opposite value. So we can say that 2's complement of a positive binary number is negative. And similarly, if we start from a negative binary number, if we in place of 0 if we take 1, then finally in the MSB position this will become 0. So 2's complement or 1's complement of a negative number, they are positive. Now again the same concept, that since for unsigned binary number we use all the bits, so that counts. If we are representing by 8 bits, then it will be 2 to the power 8, so it will be in total 256. So it will be 0 to 255. But since we are dealing here with signed binary number, then it will become again half. So half means 2 to the power 7, so it will be 128. So on the right side it will be 0 to 127, so plus 0 to 127. But here in 2's complement representation we don't have any concept of -0, because suppose if we start from 0 0 0 0, this is a positive 0, then if we take 1's complement of that, then it will become 1 1 1 1, and then if we add 1 to that 1's complement to get 2's complement, then it will be 1 plus 1, it will be 1 0. So here it will be 0. Then again there will be a carry 1, so with that one if we add this one, then again it will be 1 0. So here it will be 0. Then again carry 1, so with this one if we add that carry 1, then again it will be 1 0. So here again it will be 0. Then we have carry 1, then with that carry if we add this one, then again it will be 1 0. So what value we are getting back? We are getting 0 0 0 0 only. So we are getting the same value only. Since we are representing by 4 bits, so we will discard this carry. So if we now consider only 4 bits, we are getting back the same number, the same positive 0. So here in case of 2's complement we don't have any concept of -0, and that's why if we are representing by 8 bit, then it will be on the negative side, it will be from 0 to -128, and 0, this 0 will be same for both the sides, so it will be positive 0 only, and that's why on the negative side we have one extra value, and that's why instead of -127 it is -128. So now if we generalize by n number of bits, then it will be 2 raised to the power n minus 1 minus 1 on the positive side, that we have seen in previous 2 representations also. But on the negative side it will be 1 more, so it will be 2 raised to the power n minus 1 minus 1, and then with that we will add plus 1 since it is 1 more, so it will be 2 raised to the power n minus 1 only. Next we will be using these 2 examples, 31 and -12, to represent by using all these 3 techniques: sign, magnitude, 1's complement and 2's complement. First we have to take binary equivalent of 31 and plus 12. Here we want to represent minus 12, so we will start with plus 12 first. So this is the binary equivalent of 31. 31 is in decimal number system, and here to represent 31 we need 5 bits, because 2 to the power 5 we know is 32. So from 0 to 31 we can represent by using 5 bits. Now we will represent these two numbers by using these three techniques. So first technique is sign magnitude. So here it is given that we have to represent for all these three techniques by using 8 bits. So for 31 we can see we have 5 bits. So by using sign magnitude representation, what we will do is first we will write the magnitude part. So it's all ones in first 5 position, but we have to use 8 bits. So here it will be 0, here it will be 0, and the last bit, 8th bit or MSB will be used as per the sign. Here the number is positive. So in MSB position this will be 0. So the complete representation in sign magnitude technique or sign magnitude representation for plus 31 will be 0. So this 0 is for plus sign, or this signifies that this is a positive number. So in total here we have 8 bits. Now come to minus 12. So for plus 12 we have obtained this value 1100, but still it occupies only 4 bits, but we have to represent, or we want to represent by using 8 bits. So in the MSB position, in the last position, the value will be as per the sign. Here this was for plus 12, but the number actually is minus 12. So in MSB position we will be using 1, because we know for negative sign the value is 1. So here we have 5 bits till now. So the rest of the bits, the 4th, 5th, 6th and 7th position, we have to fill by 0. So here the from 0 to 7th, this will represent magnitude. So even if we add these 3 zeros before this number, that will not change the magnitude of that number. And then at the final position, at MSB position, we will use the value as per the sign. Since it was negative, so it is 1 here. Now we will be using 1's complement. What we have learned is for positive number, the 1's complement representation is same as the binary representation of that positive number. Now let's represent minus 12. So since this is a negative number, and for 1's complement representation, what we have learned, that first we will represent the positive number, binary representation for the positive number. So for plus 12 it is 1100, but we will be using 8 bits. So rest of the bits we will fill with 0, because we want to represent plus 12 this time first, and then of that number we will take 1's complement. So if we take 1's complement, then 0 will become 1 and 1 will become 0. So here it will be 1 1 1 1, and then 0 0, and then 1 1. So this will be 1's complement representation of minus 12. Next is 2's complement. We know again 2's complement representation of a positive number same as the binary number. So again 1 1, and then all 5 ones we will be writing, and then rest 3 positions will be filled with 0. So this is 2's complement representation of plus 31. So one thing what we can notice here, that sign magnitude representation, or be it 1's complement or 2's complement representation, for a positive number all the representations are same. But if we represent the negative number, now if it is minus 12, so what we have to do is with 1's complement we have to add 1. With 1's complement value we have to add 1. So it will be first 4 ones, then 0 0, then 1 1, and then with that we will add 1 to get the 2's complement value. So 1 plus 1, it will be 1 0. So 0 here, then we have 1 carry, then 1 plus 1 again 1 0. So 0 here, then we will have 1 carry here. So 1 plus 0, it will be 1, then here it will be 0, then all ones after that. So this is the 2's complement value. So this is the 2's complement representation of minus 12. So this is how we use all these 3 techniques to represent a negative binary number. So I hope we have understood the techniques well. With that hope, I end today's class. Thank you.